Good morning.
Yeah, good morning, sir.
Yeah, very good morning. Yeah. Okay. Okay. Yeah. Is the screen visible?
Yes, sir.
Yeah. Right. Okay. So any questions in the last lectures on processes? We almost completed the process in the last lecture, right? Uh, so and one more thing is that actually, yeah, as you, I think you might have received the mail and instructions from the institute that I think you will be back. Most of you, not most of you, all of you are supposed to be returned to the institute before this end of this month, right? And another thing is that the exam will be the physical exam. So yeah, anyway, your midsem is also a physical exam, but this time you had to write the exam physically in the room, like in the Nalanda complex and all. So that's what instructed. So I think all of you are aware of that. Anyway, I'll just send an email also for the sake of uniformity across all. Okay, so that's all about this one related to the exam and the other things. Okay, so then let me start that where we have like left in the last class. So we are discussing about pipes, and so as we have seen, yeah, prior to that we are discussing on the IPC, that is inter-process communication. And in that inter-process communication, it's nothing but communication between two processes. And the more emphasis and the mostly we discussed about the interaction between the two processes that are present within a system. And for that, we have seen, we discussed about shared memory, one mode of the interaction or like a communication between two processes. The other one is the message passing scheme, right? And in the message passing scheme also, there are varieties of ways, like how the process will communicate by using a direct way of communication, using a direct link or like indirect way of that one. And using synchronous, asynchronous modes. So various things we have discussed. And after that, we also mentioned a few ways how the process can communicate if the processes are present on remote machines. That means they are not present on the same machine. So in that case, what are the way, how does the process will communicate? So in that context, we discussed about sockets, right? A socket is nothing but the unique identity of a process that is present on a particular system, right? That unique ID consists of two parts. One is the host ID, or nothing but the machine ID where the process is present, and then a process ID, or known to be port number and all. So port number and the IP address together can be viewed as a socket. So by having a socket, pair of sockets, then through that pair of sockets, we can have a connection. That means you can establish a connection if it is a connection oriented way of communication. If it is a connectionless, then by using some other way, like having a sockets, but we don't establish a connection prior to the communication. So that's known to be datagram sockets and all. And there is another one known to be like where one can able to communicate with the multiple process simultaneously, right? So likewise, we have various ways you can able to communicate using sockets. And and the other one we discussed is RPC, remote procedure call. And so this is also like Here in this case, the way the communication happens between a process and a process that is there in the remote machine will be using just like when you are executing a function call, right? If the process is there in the local machine, or if the process is if it is present in the same machine, then you can say it's a local procedure call. Like for example, when the process is executing, you need to execute some function call, and so simply you are just passing the parameters, and then the function will be there somewhere in the as a, in the memory, and then you can execute that process and again return back to the current process. So that is the way the local procedure calls will execute. In case of remote procedure call, as the process is present or the function, the procedure that need to be executed is not present in the local machine. So first of all, you need to identify that where that procedure is available, or who maintains that, or who takes care of that one. And after knowing that one, you need to get the address, the process ID of that one, which process maintaining that one. Then afterwards, what are the parameters that are required for execution of that process has to be sent to the destination machine or the remote machine where that procedure is available. And again, while sending the parameters and all, you should be careful because the machines are very far apart, and the machines may have different conventions and different strategies or different ways to handle the data or to represent the data and all. So therefore, for taking care of that one, we use the marshalling procedure. So that way you can able to safely send the parameters from a source machine to the desired destination machine. And there, using those parameters, the procedure will be executed, and whatever the outcome of the procedure, so that will be sent back. So that was about the RPC. And then the next one is the pipes. So as I mentioned, that the pipes are used to allow or used to communicate between the two processes, right? In the like the way like you have some connectivity, some kind of like some connection between the two processes, and with that, from one end of the connection you are just passing something, and from through other end you are receiving kind of a thing. So that way the name also here can view it like a pipe and all. But here the way it is executing these pipes will be like how do you do that? Like so there are the issues like whatever we also mentioned when you are discussing about the issues when you're if you want to perform a communication using message passing scheme. What are the various issues we thought about? Similar issues here also you can encounter, like how the communication will be, whether it's a unidirectional, bidirectional, and if it is a bidirectional, then if is it like a full duplex or a half duplex. So likewise, these are the very basic issues one need to be worried about, one need to be think of when you want to have a connection, when you want to have communication between the two processes and all. And here the pipes there are two types of pipes. We'll see that what are they. And one of them is known to be ordinary pipes, and other one is known to be the named pipes. We'll see the distinction between these two. What is ordinary pipes and what are the named pipes and all. So in general, the ordinary pipes means these ordinary pipes cannot be accessed from outside of the process where it is created. We'll see that what is, first of all, the pipes has to be created by one process, and afterwards with the created pipe, you can make use of a communication from the process whichever is created the pipe to other process. We'll see that how it will be done. So here, as I mentioned, from here you can see in ordinary pipes, the pipes cannot be accessed outside the process that is created. It means that the pipe is created by a process, then afterwards that particular process will make use of the pipe for communication, right? And as I mentioned that this process cannot make use of the pipe outside the system, outside the particular process. So in this context, basically these ordinary pipes are created by a process, and it is mainly meant for communication between a parent process and its child process. Parent process and its child process. So to establish a connection or to establish the communication or to maintain a communication between parent and child process, initially using ordinary pipes, the pipes are created and then those pipes are used for a communication, or if you want to send some data or if you want to communicate to your child, then you can make use of that pipe, right? So that way the communication between the parent and child will be carried out by using the ordinary pipes and all. So that means the ordinary pipes have the limited functionality and they are mainly meant for communication between a parent and child. So beyond that, if you want, then we can make use of the other pipes known to be named pipes and all. And the range of or the scope of these named pipes will be beyond the parent-child relationship. It means that these pipes can be used to share the communication or like you can perform a communication beyond a parent-child relationship. It means that any process can send to any other process. And again, there are some restrictions are there that we'll discuss later. Yeah, then coming to the the details about ordinary pipes. So as I mentioned that the ordinary pipes allows the way of communication between ordinary pipes will be like following the analogy of like a producer consumer style that we discussed in the last lecture and all. It means that the producer will produce some item or a data or whatever, and whatever the produced items by the producer and all, it will be consumed by some other process and all. So here in case of ordinary pipes, for example, the producer will write the data or will push the data into the pipe from one end of the pipe, like known to the right end of the pipe, and the consumer reads the data or captures or consumes the data from the other end of the pipe using a read end and all, using the read end. And so with that actually can able to see that since the producer consumer problem, we are seeing that the data communication happens in only one direction. That means the producer passes the data, produce the data, and it will be given through a buffer and through the buffer, the consumer consumes or will take the data away from that. So it will be unidirectional. And here in this context, the communication process that are handling the sharing the data will be like a parent-child relationship. And here you can see here we have a pipe here, and we have both the ends. And since the pipe is shared by the parent and child, so here this pipe, when you're creating the pipe, so it have a facility to write into the pipe and somebody has to read from the pipe. So that means for writing and reading, we use a separate file descriptors. So with one file descriptor you can write into that. With another file descriptor you can able to read into the read from the file, read from the pipe and all. So you can see there is a parent and child here, and it has two descriptors, FD0, FD1, and the FD0 may be the writing part, writing end, and FD1 corresponds to the reading. So for example, here you can see that this is the write end and this is the read end. And suppose the parent here in this context, assuming that a parent want to write, and so therefore he can use this FD0 and he can able to put the data or can write the data into the pipe, and the child can use the FD1 with which he can able to read the data. And but both the parent and child has access. That means both it has the handles of both reading and writing. But depending upon the way of communications, the parent want to send the data to child, then the parent will make use of the write descriptor or FD0, and he will close or he will block or he will just don't use the right end part. Similarly, if the child is receiving the data, then the child will activate only the read end of the descriptor and the right end of that one will be blocked. So that way, even though the parent and child have both descriptors are available, they make sure that they will access the pipe only in a unidirectional way. That means the parent will write and child will read. Or sometimes suppose if the child has to send the data to parent, so in that case, you need to create another pipe. So with that pipe, the child can able to send the data using a write end descriptor and the parent can access the data using read end descriptor. So that way, the parent and child will make use of the pipes for sharing the data or communicating the data through the pipe bundle. So we have seen that these are file descriptors. It means that the pipe is nothing but a kind of a specific file where it has both read and write handles, and this file will be shared by the two processes. And here the constraint on the process will be like a parent process and a child process. And another constraint is that it's a unidirectional pipe. So therefore, if the parent chooses to write, then the child has to, by default, it has to choose the read or other way like. And in the Windows, it's known to be anonymous pipes. And here just an example you can see here. For example, you can see this is the pipe symbol, the vertical line and all. And this ls is like it's a process, right? It's a command. Ls means is used to be list out the contents in a present directory, right? List out the files. It just lists the whatever the files that are present in a current directory or present working directory and all. So that will be given by that. If you want to see that, you can use ls command. But ls command, suppose in a particular directory you have thousands of files are there, and if you use just ls command, then all the files will be displayed, and suddenly they will pop out all the files and all, and you cannot see all the files at a stage because your the display has a limited size. You can able to see only few files which are at the end. There may be 1,000 files, but your display you can see at one time you can able to see maybe as per the display size and all, you can see only maybe some 50 files. That will last 50 files. The remaining other 50 files will be like, because they will be the total number of files are more, so you can able to see only the last 50 files. If you want to that, you have to scroll it. And whereas here, if you use the like these kind of commands by using this pipe ls and then the more means actually here you can able to see that like it can able to like split the total list of files into like some set of 50 or whatever, whichever is supported by the display and all. So that way, by using this one, what happens is that these two becomes a process ls and more, and then they can able to communicate through a pipe. And with that, whatever the ls gives output, even the ls gives output of 1,000 files, and the more can able to display that files 50 at a time. Just by clicking that just by clicking, you can able to see the first 50 files, then afterwards next 50 files, so that you can able to see like the nice way whatever the files are there in a particular directory, all of them you can able to see one after another and all, like in a paged manner and all. Right? So that way you can use here in this case ls is a process and more is a process and all. And here whatever the outcome of ls is given, the 1,000 files, so that will be taken as input, and the more now it can organize the way the display will be like, it will be convenient for the user. So this is just to illustrate that actually how the two processes will communicate using the pipe and all. So this is just an example just to illustrate that how the process will communicate. So these are the ordinary pipes, and as I mentioned that ordinary pipes has limitations because here the communication is restricted to between a parent and child and unidirectional, right? And so you can see the example of ordinary pipes, the like illustration with the code, appropriate code here and all. And if you go through that, it will be, it's very easy and all. You can see here, assuming that like the buffer size equals to 25. And then there are, we are defining a read end and write end at 0, 1. And then you are just you are writing the message with this buffer size as a suppose you want to write if you want to send greetings from a parent to child, for example, a parent created parent want to send this particular string greetings to a child process. So we'll illustrate that how you do that by using pipes. And here that means here the write message has to be used by the parent and the read message has to be used by the child and all. They are file descriptors and all, just they are declared over here. And so this is the like PID, like a process ID. And then here you can see that we are creating a pipe here. It's not in the Unix, the creating a pipe will be done by using the command pipe with the file descriptor. And it returns the like some positive value, right? And if it is a negative, it indicates that creation of pipe is failed. That means a pipe creation is failed. And afterwards, if it is not negative, right? If it is a negative, then the creation of pipe is failed. Otherwise, it is the pipe is created. Once the pipe is created, then we are forking a child, because here the ordinary pipes are used for the communication between a parent process and child process. And here in this example, we just want the parent process want to send the string greetings like this message to the child process. Just an example purpose. So for that, first we are creating a pipe here using a pipe FD, and using this command, you can able to create a pipe. And once the pipe is created, afterward, now that means the pipe creation is nothing but just we are opening a file kind of a thing. It's just like a file with specific properties where this file can be used by. We'll see that how we'll make sure that the pipe can be used by the two processes and all, right? So we are creating a pipe. It's nothing but just creating the abstract file and all. And afterwards, we are creating a child like fork. We are calling a fork system call, and child has been created. And afterwards, we are checking that if the PID is less than 0, because here, as we know that when you are calling a fork, where a child process will be created, and then in the parent process, the PID, the fork returns the PID of a child, whereas in case of child, the fork process returns 0. Right? And here this is the first check to see that whether whether the fork is successful or not, right? If the PID is less than 0, it indicates that the fork is not successful. If PID is greater than 0, it means that it's a parent process. We are allowing, that means we are writing the code related to the parent process here. If PID is greater than 0, it means that only the parent can able to enter, because it happens only in the parent process, PID greater than 0. So the parent, what is supposed to do? It already created a pipe with the two ends, read end and write end, right? And the parent has to write something into that. So therefore, it will close the read end. You can see that close the read end using a file descriptor. And afterwards, whatever it want to write, it will write using this file descriptor write end. Whatever the message is there, write message. Write message is already here there. It's nothing but greetings. It's already entered into this array. That means you are writing that. And then just mention the size of that message, size of that particular message. Then once the writing is done, then you close the writing part. Then you close the right end of the pipe, because it means that the parent is I think no more want to share. Only just want to send this particular string greetings message to the other end. And then afterwards, since it is done, then afterwards the right end also will be closed by the parent. Else means here you are checking that PID greater than 0. If PID greater than 0 means then the parent will do this, and afterwards then the child one. Else means here PID is not greater than 0. It means that PID will be, because already less than 0 is checked. So then the PID will be 0. That means child process now will do that. So child process, what it will do? Its job is to read from the file, read from the pipe. So first it will close the right hand part like in the child. And afterwards, using a read, you can see that it will read the message. It will read the message. And then once it has read the message, then it just shows that actually it just printing, just to show that what is the message it is. And then closing the read end. So that way you can see here using this pipe, one can able to, the parent and child can able to communicate. Then the named pipes, as I mentioned, that the scope of the named pipe is much beyond compared to the ordinary pipes, because ordinary pipes are limited to the communication between the parent child, but whereas named pipes is extending the scope of the communication beyond the parent child process. So therefore it has the more features, the named pipes are more powerful than ordinary pipes, and the communication is bidirectional, right? And no parent child relationship is required. And several processes can use the same named pipe, whereas earlier one, the pipe, ordinary pipe, whatever is generated by a parent, only that parent and its children can use that. And so these named pipes are supported by both Unix and Windows and all. And compared to Unix, the Windows named pipes, they offer more features and all. And these are some of the features, important features. Like in case of Unix, these named pipes are viewed as FIFO. File, and using this MKFIFO, you can create a file. That means you can create the named pipe. Then these are the just a file operations with which you can able to access the file. Like if the file is already there, then you can open it, then read, write, and close. You can do that. It's a bidirectional, but half duplex. That means only one communication is possible at a time. Simultaneous transmissions are not exist. And again, one more limitation with the Unix FIFO named pipes are like inter-machine communication is not permitted. It means that the communication is only between the process of the same machine. Like whereas in case of Windows, it has a richer communication mechanism than Unix and all, like create named pipe and all these things you can do it, full duplex and intermission. Yeah, it is just like whatever, whichever is not exist in the FIFO that can be supported by the other ones. So this is all about the like related to the pipes and all, and with which we can stop this one and we can move on to the next one. So the next thing that we are going to discuss is just an extension to the process, right? Threads. And so far we discussed about a process, like various aspects of a process. We discussed the communication between the process, how the process will move, will transition to various states and all. So all these things we discussed. And now coming to the like more the internals of the process, known to be threads and all. We'll see what is thread and various aspects of this and all. So under this, we'll try to discuss about these things, overview what is thread exactly, right? And multi-core programming. So why you are mentioned here the multi-core programming in the context of threads and all? Because if application process is a multi-threaded one, then one can able to exploit the multiple cores or the multiple processes present in a architecture in a system and all, right? And we'll see that how it will be multi-threaded models, like how this multi-threading concept, like a process. So far we discussed about a process and a multiple process. There are many processes will be there. And how do you coordinate? How do you schedule that? And so those aspects we had discussed. And now the multi-threading means in a process itself, there are multiple threads is possible. Here, first of all, thread means it's a sequence of execution. So far we are viewing that a process means a single sequence of execution is possible or is present in a system, in a process. And suppose if you make the process can have a multiple sequence of executions, so it means that a process can able to run simultaneously by multiple executions or multiple processes and all. So that concept is known to be multi-threading. We'll see that what are the details and all, like how to implement these multi-threading models and all. Suppose a process has 4 independent threads or 4 threads, where that means 4 execution sequences are possible. Independent execution sequences are possible. So it means that the same process can run on 4 processes, physically 4 processes. So that's what the concept of multi-threading and all. So how do you implement that? So for implementing this multi-threading, we use the thread libraries the same way, like for execution of process or for making use of operating system and all, we use a library functions known to be APIs and all. So with which the application programmer will make use of those APIs to take the services of operating system. Suppose you want to use a particular device, take the input from a keyboard, or like you want to display something, or you want some access the file from a disk or something. So all these things where the operating system involvement is required and all. So in this case, the user application programs cannot access directly those operation system routines. So they make use of some function calls or functions supported by at a user level known to be application programming interface API. So with those functions, they make use of the operating system services. So similar to that, for implementing the threads and all, like for creating the threads, for managing the threads, and for using the threads and all. So they also need the operating system services or system services and all. So in that case, what are the various the thread libraries that supports the management of threads on the system and all. And another thing is implicit threading. So implicit threading means actually here the concept of implicit threading means, suppose if you want to, if you are right, you have application program, and we know that an application program, if you want to make it like a multi-threaded process, the application that means the programmer itself, generally the programmer itself will write the application program in a multi-threaded manner. That means he will split the program, or he will try to divide the program into like multiple sequence of executions, where those sequence of executions can run parallelly without much interaction. So that is known to be explicit threading. It means that the user or application programmer will introduce the threading, or will create the threads, or will place the threads inside the program so that the program can able to run on a multiple threads. It's not to be explicit threading, but writing or introducing explicit threading is a normal with a finite number of threads, with a limited threads and all. It's fine. It can be done. But as now the programs are very complex and all, so you need to generate so many threads for making the program to run in a very efficient way. So in that context, the application programmer to introduce several threads and then monitoring them and then writing a program using the several threads will be difficult, very complex. He has to see that where the thread is generated and how the execution is happening, and is it somewhere related or is it somewhere intersecting with some other thread. So all these things has to be looked after. It will be very hectic for application programmer to handle all those things. So that's why the concept of implicit threading means here in implicit threading, the programmer will do some explicit threading to some extent, right? And afterwards, when the program is compiling, then the compiler will introduce the threads like wherever it's required and all. Wherever you feel that, yeah, there is some parallel activity or there is something can happen like loops or whatever, if they are there, then the compiler will automatically will introduce the threads so that you can so that the user need not, or the application programmer need not bother about introducing threads at all points and all. So it's known to be the implicit threading. It means that by automatically by machine, that means that a software will introduce the threads and manage the threads and all. So it's known to be the implicit threading. So this reduces the burden on the application programmer and all. Otherwise, the application programmer has to introduce as many threads as possible, and again managing them and again tracking them. It will be very difficult while writing the programs. And then the threading issues. So having this by introducing a concept of threading for execution of a process and all, there are various issues that come into the picture and all. So we'll see that what are the various issues by introducing a concept of multi-threading, like how to resolve that, right? So those things we'll discuss under this, like threading issues and all. We'll see that. And finally, how the operating system will support this threading. Like with an examples in case of Windows or in case of Unix operating system, how this threading is supported, right? So these are the various things we'll discuss under this. And yeah, these are the same, the objectives, the overall objectives of this under this topic we'll try to discuss about. We'll introduce first the notion of a thread. What is meant by thread, first of all? And we know that if you want to define a thread, means it's a fundamental unit of CPU execution. Fundamental unit of CPU execution. So far, what we learned or what we come across is that if you want to run a process, if you want to execute a program, and when you double click that and that code, the program will be brought into the main memory and it becomes a process. And then the resources will be allocated to that, and then it will be given for CPU for execution. Then afterwards for IO, all these things happens and all. So in all the cases, we will assume that a process is nothing but a sequence of instructions, and these sequence of instructions are executed by CPU one after another and all, right? One after another. So that is nothing but so in that case, the normal thing so far, whatever we discussed, you can view that as a process having single thread of execution. A process having a single thread of execution or only one thread of execution. So it means that given the process to the CPU, then the CPU will start execution of the instructions one by one in a sequential way. And in the process, actually, if there is a conditional statement, then again it will go to the desired location. From there onwards, again the instructions will be executed in a sequence. So if you look at the whole program, the sequence, the way the instructions are executed will be follow certain execution sequence, and with that the program will be executed or a process will be executed. So that kind of the execution of a process known to be a single thread of control, or you can say that it's a single execution sequence. Suppose if you allow a program to run like parallelly on a multiple cores, like by providing a multiple sequence of executions, for example, then you can say that it's a multi-threaded program. That means, for example, you can see that there are several examples. Suppose if you write a code, simple C code, and in that, suppose we have some different functions were there, and if the functions are not interacting, for example, then one can able to run those programs. Suppose, for example, you have a sequence of numbers, right? And then with one function, you are computing a mean of the sequence of numbers. And with another function, you are computing some other statistical parameter like the mode or whatever. And other one is median, something like that. If you do that, suppose there are three operations need to be performed on that. So you can perform those three operations on three separate functions, right? And where those functions and all, they don't interact because the computing a mean and computing a median and computing some other mode and all, so they don't interact at all. So you can write these three operations as three separate functions. And anyway, the main function will be there to take care of all these things, like to compute all these things. Like you can view this particular program as a main function is one thread of control. And then when it's the execution of that one, when you are calling these functions, each function can be treated or each function can be viewed or can be created under a particular thread, so that you can call these three functions in three separate threads. And whereas suppose, for example, your computer has, for example, a quad core system, it means that four processors are available. So where your main thread can be run on one processor, and when you are creating a threads for these three functions, like a mean function, like a median mode, for example, these three separate functions, if you write in the form of three separate threads, for example, so you can execute these three functions parallelly, right? That means when you're calling, when you are one on one processor, you are running the main function, and then within a main function, you can create these three threads where each thread handle a separate function and all. And those three functions can able to run on the three other cores, because now you have a support of four cores, a quad core system, where you can run these three functions parallelly. So now you can see that you are running only one program, one process, but that process supports four execution sequences. And if the hardware supports, if you have a hardware has enough number of processors, you can able to run all these four threads simultaneously on the system itself, on the same system. So that's what the concept of like a multi-threaded system and all, right? And so then, yeah, that's what we'll see that how it will be. And then, like you can see that APIs to support this multi-threading, because if you want to perform that, creating the threads, managing threads and all, so therefore we require the support of operating system, or we can require the support of some library functions and all. So for accessing those library functions, operating systems, you can use APIs like application programming interface, where it provides some function definitions. So with that function definitions, you can able to make use of that. Like these are the examples of that one. Supported APIs like pthreads, like POSIX operating system, then Windows, Java threads and all. And there are, as we already mentioned, like implicit threading and all. We discussed like what is meant by implicit threading, what is meant by explicit threading. So just an example I have told you, like for example, you are writing a code where you need to compute the mean mode and like median and all. And here the user can introduce the threads, because user will know that there are three separate functions, they don't interact at all. So he can write these three functions in a three separate threads. And however, the program starts with a main, that is another thread. So therefore, the program contains four threads, and this entire thing is clearly written by the application programmer, right? So this is known to be explicit threading. That means the program itself is creating the threads or managing to create threads inside the program. And then the program will run parallelly on the quad core system. So this is known to be like explicit threading. But this is a simple example has shown, I just mentioned. So therefore, it appears to be simpler. But when you come to the actual real-time programs, where the programs are very, very complex and all, several things are involved, several activities are involved. So in that context, writing a multi-threaded program with a sufficient number of threads in the application programmer has a difficulty and all. He has to like tracking them is very, very difficult. Maybe he may introduce at one level, he may introduce some finite number of threads, but at a local, the compiler or the system can automatically create a threads whenever a threading can be possible. Whenever there is some parallel activity or like there is a scope of threading can be done. So then it automatically create threads, and the job can be done by exploiting by using a multiple process. And then once it is finished, then you can go on likewise. So it's known to be like implicit threading. So we'll see that how this implicit threading can be possible, or what are the various strategies for that. And also various issues related to multi-threading, we'll discuss that. And then the operating system support. So these are the broader objectives, and we'll discuss this. And coming to the motivation, as we have seen, we'll see that coming to the motivation, the most of the modern applications are multi-threaded. We'll see that. We'll take an example here. You can see, like for example, when you see that when you are when you are editing some file, for example, using a word processor. So when you are editing a file, first of all, you are using a word processing editor, and it's a process, and you can use that process, the word processor, as a multi-threaded programmer, multi-threaded process, where you can see that there are several activities that are happening simultaneously, or it can happen that can happen parallelly. It means that you are typing something. It means that there is some input you are providing, and you are typing, and those characters, whatever you are typing, so that has to be captured. That is one activity. That means there is some keyboard interface. We are typing the data into that, typing the data, and with that that means we are giving input to the file, right? And once that, so for taking care of that one, there is one activity like fetching the data from the keyboard. And afterwards, for our user interaction, whatever the data that we typed, so we can able to see that as a feedback, we can able to see from the display that whatever we typed, whether it's a correct or not. So for displaying purpose, whatever you typed, so that data has to be displayed. So that will be again another way of like another activity, right? And afterwards, when you're typing, sometimes no, you type wrong words which are not there in the vocabulary and all. So therefore, there will be some spell checker used to indicate that the typed word whether it's correct or not. So for that, there will be another activity or another like activity that takes care of that, whether the typed words are correct or not. If it is wrong, then it will be indicated by the underlying with the red colored one. And then after, when you're typing continuously from time to time, after certain time, like the contents, whatever you typed has to be saved automatically at periodic intervals. So likewise, there are like many activities that happens under a process. So one can able to write, one can able to like these activities you can able to write, or you can able to make it in the form of multi-threaded process, where one thread can look after the updating the display, and one thread can take care of the fetching the data from a keyboard, and one thread can taking care of the spell checker, and one thread can take care of the auto saving. So likewise, if you can able to split the data, split the activity into the subtask, and they can be like have independent to some extent. So that way, this word processor activity, you can view it as a multi-threaded activity, where all these things can able to run parallelly. And so with that, you can able to can able to execute the process, or you can able to run this activity very effectively by using a multiprocessor system and all, where you can able to schedule these threads parallelly across the process, so that the response time will be faster, and the efficiency will be more and all. So this is just an example how a process can be treated as a multi-threaded process, where you can able to divide the overall activity into a different subtask, where each subtask will be handled by a separate thread. And then, yeah, process. And here now we have seen the process, right? And now we know that to some extent, very like vague way, we know that what is a thread within the process and all. So compared to process creation, like the thread creation is simple. Thread creation is simple. We'll see that what is thread and all. First of all, a process creation, we know that process creation means when you create a process using a fork system call, you see that the child process will be exact duplicate of a process, the parent process initially. And afterwards, a new process want to be there, then the new process will be introduced into that. So it means that a process creation means exactly that means you have a separate address space has to be required, and then you have to replicate the contents of a process, parent process into the child process. All right. So it's like no, it's like that means the resources, all of them will be like a duplication, like a replication. Is there, suppose a parent creates like a 10 childs means that means the same resources, whatever the parent is using, a similar resources has to be used by the child process also. Like there is a more heavily intensive use of resources and all, right? and a separate address space is required, right? If a process requires, for example, 100 kilobytes, if it creates a child process of 10 child process, then each child process also required 100 kilobytes, right? So therefore, a process creation is heavyweight in terms of like time consuming and in terms of the resources it is utilizing. So everything is a heavyweight. Whereas a thread creation is a lightweight. We'll see that what is the lightweight and how the thread creation can be viewed as a lightweight compared to the process creation. Because a thread creation means actually here we are not duplicating the resources. We are not duplicating. We have only one program will be there. And within that program, we are introducing the threads. We are introducing the threads. It means that the same program, it's not the entire program is run parallelly. It's not the entire program. In that program, parts of a program which are identified and they are like fixed to a various threads and those threads are running parallelly. So, and those creation of those threads also doesn't require to replicate the code. That means whatever the code, whatever the data portion, all these things will be shared by the threads and all. They don't require a separate the data portion, separate code, separate files are not required at all. Whatever the process it's already created, the same resources will be used by the threads and all. There is no separate address space also required for the threads and all. In the same address space, whatever the process is there, the threads also will share the same address space. So that way the threads are known to be lightweight. We'll see that later with the example. It will be more clarity will emerge for you. And using the threads, it will be easier to code the complex programs also. Because if you want to introduce the threads and all, first of all, you need to visualize the program that what are the various activities are there in the program. And those activities can be separated or can be parallelized. So all those things, by doing that, you can while writing a code, given the complex program and all. So you can also view that you can split that program into the multiple entities, and all these entities can be carried out by placing the threads or by introducing the threads appropriately. Right. And then the kernels will generally, right now, whatever the existing operating systems and all, mostly they support the multi-threaded processing and all. Let's see that. Yeah, and just before going to the details, just we'll see one example, like in case of client server configuration. For example, you have a web server, and assuming that this web server is busy, like for example, a Google server or whatever it is. It's a very busy server. Like means it used to get lots of requests from several clients. It used to get heavy requests, like lots of requests, and the demand for this particular server is very heavy. So in that case, the clients will send the request will try to contact the server, will send the request to the server to fetch a particular image or particular video or particular some other documentary, whatever. So therefore, here in this context, the client server configuration, right? If the server is like, for example, like a multi-threaded one, the server is a multi-threaded one. Excuse me. హలో నేను క్లాస్లో ఉన్నాను కుమార్, నేను క్లాస్లో ఉన్నాను, తర్వాత చేస్తాను. So if it is a multi-threaded one, if you want to introduce the threads here in this server, the multi-threaded server. So here, whenever a client, because the job of the server, that the server will be like, since it's a web server, it means that it is meant for providing the services to the clients. So therefore, actually the server with whatever the server process is there, the server process, what it will do is that it will always blocked with using some command, listen command, and with that, whenever the request arrives from a client and all, it will be unblocked, and then the service will be performed, and again after that again it will be blocked, waiting for any other request and all. If any request come, the arriving a request is nothing but an event to happen. So that when that event happens, then the server will be unblocked and then perform the service. So that way the server used to operate. It used to be always in the blocking mode, and it will be unblocked whenever there is a request from a client and all. And then after unblocking, then whatever the request, it examines the request, and then based on the request, it sends the response back. And since the server is like a highly demanded server, so there will be several client requests used to be there. Suppose one client request arrives in a normal mode, then server will be unblocked, and then it will see the response, it will see the request and all, then it will fetch the whatever the request is there, then it send the response. And during that time, if there are any other requests arrives to the server and all, since the server is busy with handling the request of a particular client, and during that time, if any other request arrives, those requests will be pending. Those requests will be kept in a queue. And then after once the first client has been serviced, then the server will go into the listen mode, and again already there are pending requests are there. Then again server will be unblocked, and then it will take the next request and it will be served. So likewise, the server will, while doing that one, there will a lot of requests will be keep on pending. And so to avoid that, one way is that actually a server can create a process like whatever the new child process, and then whenever the request arrives, it creates a child process, and then it handles it passes the request to the child process, and again the main server will be again going to the accepting the request and all. So that way, whenever the request arrives, then it keep on creating a child, and the child will provide the service to the request and all. But as we already mentioned, that creating a child process is a heavy process. That means every child will again take a replica of a server address space, and it's heavy. It's heavy, right? And a lot of resources will be consumed, and a lot of memory will be occupied. So therefore, creating several child process to handle the requests from for the clients and all, it is very heavy. So other way is that suppose the server is a threaded one, multi-threaded one, then when a request arrives, then it creates a thread. So creating a thread means it's not that actually no additional resources are not required. Whatever the server code is there, the same code will be used by the particular thread. And whatever the request arrives, that request will be passed on to that particular thread. And now the thread will service that one. The thread will run, and then whatever the service request, whatever the request is there, based on the request, it will fetch the desired data and will pass on to that. Right. So likewise here the server, if it is a multi-threaded one, so whenever the request arrives, it creates a thread, and then the thread will be assigned to the request. So likewise, and creating a thread is not that difficult, because when you compare the creation of a thread to the creation of a child, creation of a thread is much faster. It's almost like in the Unix system and the Solaris system, you can able to like quantitative measure is about 30 to 40 times faster compared to a creation of a process and all, creating a thread. So therefore, thread creation is a faster, and not only that, the created threads don't take any additional resources and all. They need only the execution environment. Separate execution environment is required. All the resources, whatever the main process is there, and those process resources only will be utilized by the internal threads and all. So that way here in case of multi-threaded server, like client server paradigm, where if the servers make use of a threads and all, then it is much efficient, or it can able to provide the request at much faster rate at a low response time. It can able to do it by using a threaded, by introducing a threads and all. Yeah, now, yeah, you can see here, yeah, this is the basic distinction between the single threaded and the multi-threaded process and all. And this is a process where there is no threading involved here and all. And here that means it's a single execution sequence. So for a process, we know that a process contains a code segment, and then the data segment, and then whatever the files that are there required for the process, and also those will be attached. So these are the various resources that are required by a process and all. And then for the process to execute, at the time of execution of a process and all, the execution environment consists of stack, because when the process is executing, whatever the local variables, whatever the functions and all those things, and all the current data, current executional data will be there when you're calling a function and all, passing the parameters or the local variables that are used here. So that will be maintained by the stack and all. And the automatic operations, whatever when the process is computing, when the CPU is executing, at that time the intermediate variables, intermediate data, all these things will be stored by the CPU registers and all. So what it means is that when the process is executing, or when any execution is happening, the environment that is required for to carry out the execution will be stack and the registers, CPU registers and all. Stack and the CPU registers. So therefore, if the process is a multi-threaded process, so for example, in this case illustration, there are 3 threads for that. All these 3 threads, they have a common these resources: code segment, data segment, and then the files, whatever. So all these resources are common. All these resources are shared by all these threads. But each thread is a separate execution, right? Each thread is separate executional entity. So therefore, if you want to run these three threads parallelly, then each thread of execution requires its own environment, right? Because this thread may be executing some functions, this thread may be executing some functions, some other instructions, arithmetic operations. This may be executing some other thing. So to maintain these executions parallelly, each thread requires a separate environment or unique or individual environment is required. So this individual environment is supported by a stack, separate stack, and a separate set of CPU registers and all. Separate set of CPU. So that way, if you have a multiple threads that are running parallelly, each thread should have these things are distinct, like these things are independent, and whereas all these things are common and all. So that way, when you look at a process to a threads and a multi-threaded process, suppose this process creates suppose 3 childs, for example. So in that case, all these things will be replica. These things, whatever the code, data, files, and all, whatever parent process, all these things will be replicated to the child also. And then whatever the data, whatever the memory size that is required, the entire the same memory size is also required for other things also, for other child process. Whereas for threads and all, even though the process has 3 threads here, for example, so they don't need any separate address space. All the threads are present in the same process. They share this code segment, data segment, all the files, whatever is required. The only distinct things that are required, because it's obvious, because each of them are the separate execution. Like they can able to run, if you have a chance, three can able to run on 3 CPUs parallelly. So when each of them run on a particular CPU, it requires obviously the registers, whatever is there under that particular CPU, will be used by this particular thread. And at the same time, the stack also, a small segment of memory is required to track the current execution. So likewise, in case of multi-threaded process, these segments are common. Like most of the code, data, all these things are common across all they share it. The only thing, the distinct things that are required will be the execution environment, right? So this is the basic distinction between a concept of threading versus a concept of process and all. When the process create a child, means all these things are replicated. Like so that way, the threading will be efficient in view of like resource sharing and all the aspects and all. Yeah, these are the benefits of the multi-threading concept. Responsiveness. Because responsiveness means, for example, if a process is a multi-threaded process, and then assuming that, for example, a multi-threaded process, but this is executing in a single process, only one processor is there, and now one thread is executing, and in that thread of execution, suppose the thread is using some blocking system call. It means that actually there is some IO statement was there. So IO statement means that the input has to be given. Suppose the input that is required from the keyboard, for example. So at that time, since the system call has to be placed for taking care of that IO, but the system call is a blocking system call, because that IO has to be taken from the keyboard, and whenever the user will give the input, then at that time only the input will be passed to the program and it will start its execution. So till that point, the program has to be blocked. That means the execution has to be blocked. So in that case, the normal operating system, what it will do, the process, because it's only one single execution sequence, and somewhere if it is a blocked, for example, so at that time the entire process will be blocked, and then the operating system will fetch some other process. It will give it to the CPU. Whereas in case of multi-threaded process, for example, if it is a multi-threaded process, then what happens? Suppose if there is in one thread of execution, if there is a blocking system call, then that particular thread will be blocked, and then the operating system can able to provide the execution to some other thread in the same process. Some other thread in the same. Suppose, for example, the time quantum is 100 milliseconds, for example. And suppose if there is only one sequence of execution, then at the 10th, suppose at the 15th millisecond, for example, you have IO call. You have some IO required. IO statement was there. Then even though the time quantum of 100 milliseconds, but the process will be removed because it's a blocking system call. So it will be removed and some other process will be given. Instead, if the process is a multi-threaded process, for example, And if one thread is executing at the 15th millisecond, you have a blocking system call, then the thread will be suspended and the next thread, the second thread of the same process will be given access to the CPU and that thread will be executed. And there also, if there is a blocking system call, then the other thread will be there. So likewise, if there is a threading and all, then you can able to like even though the one of the thread is blocked, but the whole process is not blocked and all. So that way it will be more responsive. Suppose, for example, you have interactive programs are there. So where if you can able to make that the user interaction with one thread and a computation with some other thread and the blocking will be some other thread. So likewise, if you make the program has to be like a multi-threaded where the user interaction also required. So in that case, you can able to like if you multi-threaded one, even though a program is a computational at some point of a time, but that is given to a thread, that thread will operate only finite amount of time. Afterwards, again, you need to have some interfacing thread has to come into picture. Then the user can able to give the input, a user can able to see the execution and all. So that way, by having a multi-threaded concept where the program will be more responsive, it means that it will not block at all. So all the threads have been given a chance, and even the user interaction also can be better handled by using the multi-threaded one. And another one, resource sharing, already I have mentioned, like we already discussed about what is meant by resource sharing in the context of threading. And economy, here economy means it's not with the cost and all. Here economy means with respect to the time efficiency with respect to creation of a threads and switching of a threads and all. Like as we have seen that thread creation is simple, as we already mentioned, some statistics I have given, like it's about 30 to 40 times faster compared to the process creation. Because the process creation involves like you have to create a separate memory image and again you have to copy that into that and all these things are the part of a process creation. But whereas thread creation, nothing. Thread creation means only that environment you have to create, right? Other than that, it's again a part of a process and all. And at the same time, the thread switching is also faster compared to context switching. But here in case of thread switching also, you need to have saving and then the reloading of the thread control block is required. Similar to the process control block, whatever we discussed, similar to that, if a process contains a multiple threads, to maintain these threads, we have a thread control block is required, right? Similar to that. So, but the thread switching is faster compared to context switching. And scalability is nothing but suppose you have a multi-threaded process, you can able to run faster because on a multi-processor systems, because you have multiple cores are available. So one can able to run the process if you wish, if it is required. The same process can be run across the multiple cores. So with that, the process execution time will be optimized if required. So it means that you can exploit that. If in case of multi-core architectures and all can be very much exploited by using the multi-threaded concepts. So yeah, now yeah, it's time up. So we'll stop here and we'll continue this lecture on Monday.